Welcome back. So, over the last few deep dives, we've been tracking what really amounts to an immense global shift.
It's a huge one.
Yeah, exactly.
Yeah.
Artificial intelligence is moving out of the laboratory, and it's rapidly becoming infrastructure-level technology.
Right. This isn't just a trend anymore. We're really talking about a replatforming of the global economy. I mean, fundamental changes to how industry works, to supply chains, and, eventually to public policy.
Absolutely. And today, we're concluding this whole series by looking at the 10th and final development that's set to reshape this landscape.
And it's been quite a journey.
It has. I mean, just to set the stage, remember the sheer scope we've covered? We've talked about everything from foundation models as a service, self-supervised robotics,
all the way to AI-driven drug discovery and federated AI networks.
It's this vast, interconnected digital brain where every single component has its own specialized role.
That's a great way to put it.
And today, we are diving deep into what might be the most specialized, the most computationally demanding component of all, quantum accelerated machine learning, or QAML services.
Right.
This is all about providing cloud-based access to quantum systems for these very niche, very demanding machine learning tasks. So our mission today is pretty clear.
I think so.
We're going to define what this quantum niche really is, explore why the timing for this is now, and then we've got to tackle the very real technical and, frankly, economic challenges standing in the way.
So to really get what QAML is, you have to realize that this is first and foremost a cloud service. We're talking about vendors providing API access to actual quantum processors.
Okay, so these are real quantum computers we're tapping into.
Real quantum processors, yes. Things based on, superconducting qubits or maybe photonic systems. But, and this is the key, they're highly tailored for specific machine learning subtasks. They are not general purpose computers.
They're definitely not running my operating system.
Not at all. So if they aren't powering, your everyday apps, what is their sweet spot? What kind of task justifies bringing quantum mechanics into the picture?
That's the question.
Well, the quantum advantage really emerges when you're dealing with specific computational bottlenecks. We're talking about highly specialized subtasks, like, say, sampling from immense high-dimensional distributions.
Which is critical for things like generating high-fidelity synthetic data, right? Or analyzing really complex financial models.
Exactly. And what else?
You also see it in solving these incredibly complicated combinatorial optimizations.
Think about the classic traveling salesman problem, but, scale that up to a global logistics network with thousands of variables.
Wow. Yep.
And finally, QAML is also used for training something we call quantum-inspired kernels. These are specific algorithmic pieces that are designed to find complex patterns in data that classical machine learning. They just often misses them.
It gives a better foundation for the whole AI model. That makes the niche very, very clear. But, when people hear quantum computing, the assumption is usually that it's still decades away.
That's the common perception.
So what does the research say about QAML's immediate timeline?
The sources we're looking at are optimistic, but they're also realistic. Right now, QAML is firmly in the research and development phase, and that's likely going to be the case from 2025 through, say, 2027.
Okay, so still a few years out from prime time.
But because of this hybrid approach we're going to talk about, the projection is that these services will start moving into niche, high-value commercial use cases around 2028 or 2029.
So it's coming fast, but only in these very specific, economically justified areas.
Precisely.
That brings us squarely to the technical driver, right? The quantum advantage.
Yeah.
Why does it matter to invest in these incredibly complex systems right now, especially when classical chips, your GPUs, your TPUs, they keep getting exponentially better?
What's so fascinating here is that QAML isn't waiting for perfect, error-free quantum computers. That's a different, much longer-term goal. This technology relies on the systems that are available today.
The so-called NISQ processors.
Exactly. And for you, the learner, it's worth knowing what NISQ stands for.
Let's hear it.
It's noisy intermediate scale quantum. And the key word in there is noisy.
Right. Meaning they have errors?
Lots of errors. But they are just powerful enough to show a critical advantage in these very targeted subroutines. The goal is simple: leverage the intrinsic parallelism of quantum mechanics to massively speed up specific calculations.
Like the sampling and optimization we mentioned.
Within a much, much larger classical machine learning workflow.
So it's not a replacement for classical computers. It's more like a hyper-specialized accelerator card you bring in for the absolute toughest computational fights.
That is the perfect analogy. And that hybridization is what gives it this critical performance edge in fields where, every single percentage point of optimization gain can translate into billions of dollars.
So we're talking about sophisticated global logistics, or the very sensitive processes in modern cryptography.
Exactly those.
And this is where it gets really interesting for me, because the impact is twofold. Commercially, this lets those optimization-heavy industries get speed improvements on these incredibly difficult challenges, what are called NP-hard subproblems.
Right, and if we connect that to the bigger picture, it also serves this vital role as a research testbed. I mean, these NISQ services are the only viable environment we have for testing the complex quantum algorithms that will eventually need to scale up to future fully fault-tolerant quantum computers.
We have to figure out the coding structure now.
We have to.
So let's nail down that concept of NP-hard problems, because they're really the whole reason QAML even exists. Why are they such a computational nightmare?
Well, the official definition is, it's pretty complex. It stands for non-deterministic polynomial time.
Which doesn't help most of us.
Yeah, exactly. But what it really means conceptually is, think of it like this. NP-hard problems are the ones where if someone just hands you a potential solution, verifying if it's correct is actually pretty fast.
Okay, so checking the homework is easy.
Precisely. A few minutes, maybe. But actually finding that initial solution, that can take an unfeasibly long time. For a classical computer, the time it takes often grows exponentially with the size of the problem.
Like optimizing the routes for thousands of delivery trucks all at once. The number of possibilities is just astronomical.
You've got it. QAML targets that really complex finding stage. It provides a kind of shortcut around the most brutal computational bottlenecks.
So QAML is the tool designed to write the complicated answers to the absolute hardest homework problems. That transition brings us to the practical side of things. When this kind of speed and power actually hits the market around 2029, where are we going to see the biggest impacts?
The computational power is it's unprecedented. It enables these high-fidelity simulations and complex problem-solving scenarios that were just impossible before, for classical computers alone.
And the list of industries this touches is immense. I mean, you take manufacturing and logistics, QAML could optimize these incredibly complex supply chain networks. We're talking true route planning, inventory management, resource allocation, all across massive global systems.
And it would minimize costs and maximize throughput, basically in real time.
Then there's financial services.
Oh, for sure. You'll see enhanced fraud detection systems that operate at speeds current machine learning just can't touch, identifying complex patterns and anomalies across billions of transactions in milliseconds.
And in healthcare and pharmaceuticals, QAML could significantly reduce the timelines for drug discovery. That's a process that currently costs billions and can take over a decade.
A huge potential impact there.
And we can't overlook the foundation of modern life, right? Energy and utilities. QAML could help better forecast energy consumption patterns and critically optimize power grid management.
Which would make our whole electrical infrastructure far more efficient, more resilient against, demand shocks and things like that.
There's also a fundamental defensive need for this in cybersecurity.
A huge one. We already know that future fully fault-tolerant quantum computers pose a massive long-term threat to our current public key encryption.
The kind that protects almost all of our data online.
So QAML and the algorithms we develop using it will be integral to creating the countermeasures we need now, things like PQC or post-quantum cryptography.
And QKD, quantum key distribution.
Exactly. These are essential to guarantee the security and integrity of our global data against those future threats.
That's a massive macro picture.
Yeah.
But how do these industry changes actually benefit you, the individual listener?
Well, the changes flow directly to you. First, those enhanced fraud detection systems we just talked about, they're going to better protect your personal finances. They make it much harder for unauthorized access to happen in the first place.
Which is always a core concern for everybody.
Always. Second, in healthcare, QAML's ability to process complex data and imagery much faster will mean earlier disease detection through better medical imaging analysis and more accurate diagnostic tools.
Which leads to far better patient outcomes.
And finally, there's the personalization factor that drives so much of our online life.
Right.
QAML can process these enormous data sets much faster than traditional machine learning. Remember that speed up in sampling from high-dimensional distributions?
I do.
Well, that translates directly into highly accurate, real-time, personalized recommendations in basically every sphere, e-commerce, what you watch, customer service, all of it happening with greater fidelity and speed.
That ability to process incredible complexity is clearly the advantage. But this kind of power always has a cost, which brings us to the really serious roadblocks preventing true industrial-scale quantum adoption. If this is all so revolutionary, why isn't it just replacing classical computing right now?
The approach to scaling is the immediate answer. QAML services are, in fact, designed for scalability, but they're built entirely around that hybrid model we mentioned earlier.
Could you walk us through that hybrid model with an analogy? How does it share the load between the classical and the quantum parts?
Sure. Think of the classical computer, your massive GPU or TPU cluster, as the backbone. It's handling, say, 95% of the machine learning process, the massive data storage, the iteration loops, most of the training.
Okay.
The quantum processor, the QAML service, is the hyper-specialized engine that you only bring online for those specific NP-hard subroutines.
So it's not running the whole race. It's just there to win the single toughest mile.
That's it, exactly. The quantum processor manages the quantum circuits and the data encoding, and it integrates, hopefully seamlessly, with the existing, highly scalable classical infrastructure.
It's smart, but it also exposes the fundamental limits we're facing.
So this raises the big question. What is preventing true, widespread industrial-level scaling right now, even with this clever hybrid approach? There are 4 critical challenges. The first is hardware reliability.
The noisy part of NISQ.
The noisy part. These devices are extremely sensitive to temperature, to vibration, which causes errors. We call it decoherence. Very, very quickly. Getting any usable results requires incredibly sophisticated and robust error mitigation techniques. And that complexity adds time and it adds cost.
And that leads right into the second challenge, which is the business case. Why would you invest millions in this noisy hardware?
That is the cost-effectiveness problem. We have to be able to demonstrate a crystal clear return on investment, a proven ROI that definitively beats the existing incredibly powerful and highly optimized classical GPU and TPU clusters.
And those are still getting faster and cheaper all the time.
They are. For QAML to succeed, its niche speed-up has to translate into overwhelming economic value in logistics or finance or materials science to justify that massive initial cost.
The third challenge sounds like a fundamental data science problem. If the quantum engine is so fast, we've got to be able to feed it data just as quickly.
We must, but we can't. Not yet. This is the data loading bottleneck. The process of efficiently encoding huge amounts of classical, everyday data into a suitable quantum state is incredibly slow right now.
So if you can't feed the quantum computer data fast enough,
the quantum speedup itself is meaningless. It's like having a Formula One engine stuck in a traffic jam of data loading. A ton of research is focused on speeding up these data prep circuits.
And the final challenge is a critical societal one, and it's about access and equity.
That's the digital divide. Because of the complex infrastructure, the highly specialized talent you need, the significant initial cost, QAML services might only be accessible to a handful of very large players.
Major tech firms, governments, massive financial institutions.
Right. And if only a limited number of entities can access this QAML-enhanced power, it could potentially accelerate existing socioeconomic disparities. It could concentrate innovation in the hands of the very, very few.
So, synthesizing everything we've covered today, and really across this entire series, what does QML's specific status, this powerful, niche, yet noisy technology, tell us about the competitive landscape of AI by 2029?
I think the ultimate insight here is that QAML isn't replacing classical AI. It's defining the future high-stakes areas that only these quantum hybrid models will be able to touch. It offers a path to handling problems that were previously just intractable.
But its competitive position really hinges on solving that economic challenge.
It's all about proving the ROI of noise. If we can reliably get those quantum speedups despite the noise, this technology is going to dominate fields like global logistics, high-frequency trading, and complex materials research.
In stepping back to the bigger picture from all 10 developments we've discussed, from foundation models to privacy-preserving networks, it is so clear that AI is going to be a true ecosystem by 2029. We're moving beyond these isolated research breakthroughs.
I agree. The 10 developments we've outlined really constitute the most consequential levers for competitive advantage, for societal impact, and for regulatory evolution on a global scale. They represent a blend of massive scale, privacy-preserving collaboration, and with QAML, this domain-specific, hyper-accelerated reasoning.
What stands out to you in all this? The acceleration of AI is undeniable, and it's now fully quantifiable in terms of this infrastructure development. But as QAML really demonstrates, The hardest parts of this transition, they aren't just technical, they're organizational and ethical.
Absolutely.
Governments, enterprises, the research community, they all have to coordinate on standards, on safety protocols, on ethical guidelines to make sure that this rapid acceleration of AI, particularly in such a powerful and exclusive domain as QAML, delivers broad, inclusive benefits. Because if we fail to manage the costs and that resulting digital divide, the benefits of what might be the most powerful technology yet will only ever accrue to the very few. And that is the ultimate goal, isn't it? Ensuring access and mitigating the risks that come with this kind of tremendous power.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.